In the previous class, we were looking at the concept called as reflection coefficient, right? And we understood that there will be two components. One is forward, one is reverse. And whatever gets reflected, we try to take a ratio of the forward to the reverse. So, and we calculate what is called as a reflection coefficient over there. So we were okay. I think we just have drawn this particular circuit showing that Vs is a supply, Vl is the voltage across the load. So the forward wave is denoted by Vs e to the power minus gamma into L, where L is the length of the line, and Vr e to the power gamma L is the reflected part. Now, if I want to write what will be the voltage across the load, right? So therefore, I can write, therefore, VL, voltage across the load, should be equal to, it's a sum of both components. First component is Vs e to the power minus gamma L, plus the second component is reflected, Vr into e to the power gamma L. All right, so let's call this as equation number 1. Right, let's try to define the rho now. So rho is equal to reflected wave by the load. This is the definition. Reflected wave by the load divided by the incident voltage on the load. So if I try to replace the terms by the equation, so the reflected component is nothing but Vr e to the power gamma L. All right, all divided by this is Vs e to the power minus gamma L. All right, so let me try to take the e to the gamma L, which is present in both numerator as well as the denominator, right? I'll try to take it to the numerator, right? So that is, so let me try to define this. Rho is equal to, this is Vr by Vs, and e to the gamma L, which is in the denominator, goes to the numerator as e to the power gamma L. Already there is a e to the gamma L, so this becomes e to the power 2 times gamma L, right? So that's the rho. Let's call this as equation number 2. Now we know that the gamma is a complex number, right? So e to the power 2 gamma L, which is in equation 2, is a complex number, right? So e to the power 2 gamma L results in a complex number. So this, the rho becomes a complex number, right? So this implies, we'll try to look at the RHS, okay? So as the right hand side of equation 2 is, it's complex. I understand that this is complex. This means the rho has to be a complex. Complex numbers can be represented in two various formats. So the one of the format is called as a polar format, where you write a magnitude. I denote that as a magnitude rho into e to the power j, and you see some angle should come. Already I have used theta, etc. So I'll use the psi, e to the j psi. So magnitude of rho is the, this is nothing but, this is the magnitude of rho, and this psi denotes the angle or the phase of the reflection coefficient. So we will note the same thing when we solve the problems on the Smith chart. We will be able to calculate the magnitude and the phase of the reflection coefficient. All right, now, so we already know that from the equation. Let's try to write the current. Okay, so, but let me try to write the current through the load. Okay, so load current IL is equal to, this should be voltage across the load. So if you look at the circuit we wrote, voltage across load is VL. VL divided by the impedance, that is Z. Okay, so divided by z naught. So how do I calculate that? This should be, right, VL, I'll substitute what we already have calculated just now in the previous equation. So that is Vs e to the power minus gamma L minus, this is Vr into e to the gamma L all divided by z naught. That's the equation for current. Okay, so that is 3. Now, how do I calculate the load impedance required? So, but by the definition, the ZL should be, right, it is the voltage across load divided by the current through the load. That's the actual value of ZL, right? So VL just now we have calculated. We know that that is VL is equal to, okay, let's try to write this. This is Vs e to the power minus gamma L plus this is Vr e to the power gamma L whole divided by, now I write the IL I just calculated. So that is Vs e to the power minus gamma L minus Vr e to the power gamma L divided by the Z naught. So that's the IL we have calculated. So let me try to simplify this by using, we can do, let us try to take the Vs into e to the power minus gamma L common from numerator as well as the denominator. Okay, so this becomes 1 plus, there is a Vr already present. I divide by Vs and e to the power gamma L and one more e to the gamma L. I get e to the 2 gamma when the e to the power minus gamma L goes up. This happens in the numerator whole divided by, once again, in the denominator also I'm going to do the same thing. But there is a Z naught. So I'll write a Z naught here into Z naught because it is in the denominator of the denominator which can go to the numerator. Okay, so we do that now, and let me take this out. Vs e to the power minus gamma L, and when that goes out, it is 1 minus Vr by Vs into e to the power 2 times gamma L. All right, so these two terms will get cancelled, right? So on the left hand side, I'm still trying to write an equation for ZL equal to, there is a Z naught into, right? You see, this term, let's try to define the rho. Already we have written the rho here. You can see that from equation number 2, Vr by Vs e to the power 2 gamma L is a rho, right? So let's try to substitute. From the above equation, we can see that this is 1 plus rho divided by 1 minus rho. So the ZL can be calculated using Z naught if you know the value of rho. Okay, so that's the equation of ZL in terms of, if you want to calculate ZL using the Z naught and rho, you can use this. But our intention is to calculate a rho. So let's do the cross multiplication, right? So that is ZL into 1 minus rho is equal to Z naught into 1 plus rho. I want to calculate rho, so let's multiply. So ZL minus rho ZL is equal to Z naught plus rho times Z naught. I'll bring the terms containing rho to the same side. Rho times Z naught plus rho times ZL is equal to ZL minus Z naught. So rho times ZL plus Z naught is equal to ZL minus Z naught. So that implies, right, I can calculate rho as ZL minus Z naught divided by the ZL plus Z naught. So this is what we were looking for, trying to calculate the reflection coefficient. If you know that ZL and Z naught, right, what are the values? Now you understand one thing from here, right? When we discussing the theory part before the derivation, we just guessed that the reflection coefficient is actually proportional to the, right, difference between ZL and Z naught. I can actually note, I can, it's proved here. You see that it is directly proportional to the difference, ZL minus Z0. So you see, if at all the ZL and Z0, they match, what happens? Whenever they match, you see the difference is 0, so rho is equal to 0. There is no reflection. Whereas if the ZL and Z0 differ by a huge amount, if that gap is more, right, definitely this rho is going to be more, indicating that you have a larger amount of there is a larger amount of reflection that is happening. Okay, fine. So that's what is the meaning of this. Now let us look at various possibilities, right? So of what are the various values, right? What happens to the rows for various types of lines? So let's go to that. So this is also very important concept. Okay, so whenever, for example, let's assume that ZL is equal to 0. When the load value is 0, you call it as the short circuited line. Okay. It's called as a short circuit line, right? In the sense, the load equal to 0. So you have a line, but the load is short circuit. Okay, there is no load connected. In the sense, it is a short circuit. So this is what is a short circuited. Now do the calculation. This implies in such case, what happens to the rho value? ZL is 0, 0 minus Z0 divided by this is 0 plus Z0. So the rho value becomes equal to minus 1. All right. So I know that this can be written as 1, right? 1 e to the power j pi, correct? 1 e to the power j pi, because angle pi is going to generate a minus 1 over there, correct? So magnitude of rho is equal to 1 and the psi value is equal to pi. So that's what is the indication whenever you have a short circuit at the end. All right. Similar to that, we have the next case, that is case number 2. So case number 2, ZL equal to infinity. What do you mean by this? This is open circuit. Right? That means the end of the line you have open circuit. So the load becomes equal to infinity. Okay, now let us do the calculation. So rho is equal to, right, the ZL minus Z0 by ZL plus Z0. What is the value? Can you calculate? What is the value of rho we are expecting here? Okay, so try to take, before you make the substitution, take ZL common, okay, from numerator and denominator. So this is 1 minus Z0 by ZL, okay, divided by ZL is common even in the denominator. So this is 1 plus Z0 by ZL. Okay, so ZL cancels. Now you substitute ZL equal to infinity. This is 1 minus Z0 by infinity is 0 divided by 1 plus Z0 by infinity is 0. So your answer becomes equal to 1. Right? So when I get the rho value equals to 1, right, I understand something. I know that I'm expecting this to be a complex number. So magnitude of rho is equal to 1 and the psi value becomes equal to 0. So the phase angle is 0 here. Okay. Right. Let's go to the third case. In case 3, right, the ZL is a complex load such as you have RL plus J times X. So we cannot calculate the rho value here because ZL is some arbitrarily written values. But I can understand that the rho becomes a real number. It's a real number. And the psi value will be definitely between 0 less than or equal to psi less than or equal to 2 pi. This is for sure. Okay. So these are the various cases we might face when we solve some problems, right? In the sense, if I get a real number for rho and a angle between 0 to 2 pi, it means the load connected is complex. The load connected has, I should understand that, okay, the load is complex, it will have a real value indicating the resistance, and a complex value, and and an imaginary value indicating that either capacitance or or impedance. Sorry. Okay, so that's what is the indication for this. All right, now what I do, I will try to write the equivalent diagrams. Okay, equivalent diagrams of case 1, case 2, and case 3, showing that how we will be seeing the loads. Okay, what will happen to uh, the how the waveform looks like. That's what is my point. Okay, so let me try to. Okay, so this is the case 1. I'm writing the case 1 again, once again, because I'm trying to draw its waveform. Just a second, I'll try to copy that once again. Yeah, okay. Now it's so in case 1, you see this is the type of waveform we are going to get. Right? You see on the rightmost side, I have a short circuit. ZL is 0, load is 0. And since the angle is, what is the value of psi value for a short circuited case? You can see that the value of the short circuited case 1, angle is pi. Correct? So there is a phase shift by angle psi. So that should, I should be able to visualize that here. So just note. So let me assume that the maybe one of them, maybe the red colored waveform is the incident. Okay, it hits the load, short circuited load at this point. Okay, but because of the phase being pi, right, everything should be reversed when it reflects back. You see, signal was going up, right? It was increasing. Now you see the reflected wave is decreasing. Are you okay with that? So the phase angle being 180, I am able to show it here, right? But some concept which is very familiar, which is very similar to that we studied in communication, correct? So you see that phase angle is 180 means, right? I might have, if I have a wave like this, it should change like this. It was going down, right? It should change its direction. It should go up instead of going down. So it was going up. Now the reflected wave goes down, right? And its position is reverse, right? I have a positive value. It starts from an equal and negative. Are you okay? So that's what is going to happen. We will be visualizing this kind of waveform if you use a scope to visualize the incident and the reflected waves for a short circuited line. Okay. All right. Let's look at the case number 2, wherein our intention is to visualize the open circuited case. That's case number 2. So this is how it's going to look like. I'll pasting here and let me expand. Okay, so it's very clear now. So whenever I try to do this, Now you see, let's look at the phase, right? What is the phase over there for case 2? Phase is equal to 0. In the sense, no change, right? Phase will never be reversed. In the sense, it was going up, it will maintain its direction. So can you visualize that? So I can see, right? If red is my incident wave, it is decreasing, right? In the reflected wave also, it continues to decrease, right? So because of that, we call it as a open circuited line will reflect in this particular fashion. Okay, then the case 3 comes into picture, which is a complex load. So we don't have a very specific relationship between, right, what we send and what we receive. So because of that, we may see something like this. Let me copy it in. Okay, so this is how it's going to look like. Now you see the relationship is very clear over here, right? What we can see, the waveform hits at some point, at this point, it will reflect from some other point. There is nothing, because that's because of the psi being present. Some other psi is present. It's not 0, it's not uh, any specific value. It's some random, right? Value that depends upon that. Okay, so that's how it's going to look like. Now I'll give a condition over here. So that is, if let's see VR equal to 0, that means IR is also 0. If that is the case, how do you calculate a Z naught? VR and IR will not come into picture. There is no reflection. You simply have the Vs e to the power minus gamma Z divided by Is into e to the power minus gamma Z. So you see this will cancel. So that means it is simply Vs by Is, right? Vs, Is are real quantities. So this is also real. So when there is no reflection, Z naught is real. Characteristic impedance of a line is real. That itself indicates that you don't have any reflection. Okay, so another way to do the analysis of a given transmission line. Okay, all right. So that's about the reflection coefficient. One more very important thing that we have studied, that actually has come into picture so far, but we never use this widely, but we are going to use it widely in the problems. That term is the input impedance. So whenever you see any given problem, it will be either they are asking you to calculate, find the input impedance of the line. So that is denoted as ZA. So what is this Z in? Let me try to write a simple circuit initially. So we have a resistor. Some load is connected. And right, so there is a ZL, and let's assume that this particular line has a length. That length is equal to, say, L. Now, if you look into this line from the input side, right, you will see a resistance, right, that is called as the Z in input line. So normally this impedance, whatever we call as Z in, right, that actually takes care of the impedance of this line, and this line. So it's always like that. Okay, it's a total impedance, right? Just to make you understand, I'm telling this, but exactly we don't calculate in that. We calculate it in a different. Okay, now, so we initially calculated the ZL by using the voltage at this point and the current over here denoted by IL. Correct? We had a VL and IL, divided VL by IL to get the value of ZL. Correct? Previous derivation. That was using this particular technique. Okay, now what I do, now I go slightly, I apply the similar concept, but at, see this point, at input point. So how do I reach the input point from the load? You need to move a distance L, correct? From the load end, the distance to be covered is L, but according to our convention, this is positive direction. If you move to the left, that is a negative direction. Correct? So now I am moving in which direction? I'm moving from the load towards the source. That is a negative direction for, correct? I have to move a distance of minus L from the load. Is it okay? Are you fine with that? Right. So now I'm going to use a definition or use an equation to calculate the Z in that uses this particular notation. Right. So here we write. So Z in input impedance is equal to, this is the voltage at Z equal to minus L from the load divided by the current at a point Z, which is equal to minus L. Is it okay? Now, what I do, I write the equation I calculated for ZL, but in that I keep Z as it is. At any point Z, you can calculate. So that is equal to characteristic impedance Z naught into, I'll show you what equation I'm using. Right? This equation, this one. Okay. This one I'm using with the Z naught on the top. Okay. So let me write that. So this is Z naught into, so numerator is Vs e to the power minus gamma Z plus Vr e to the power gamma Z whole divided by, this is Vs e to the power minus gamma Z minus Vr e to the power gamma Z. Okay, this is the general equation, but for this, the current situation, I need to put Z is equal to minus L because I am calculating at this particular point. So that means let's substitute the value appropriately. So Vs numerator Vs e to the power minus gamma into minus L is gamma L plus Vr e to the power minus gamma L because Z is equal to minus L whole divided by, same thing happens in the denominator, Vs e to the power gamma L minus Vr e to the power minus gamma L. Now we see the sign change happens with the exponential terms. So what I do here is I try to take out the Vs once again. Okay, so this is equal to Z naught into, in the numerator, take out a Vs. What remains, I'll write. So that is e to the gamma L plus, there is Vr by Vs. What is Vr by Vs? If you remember, that is a rho, reflection coefficient, reflected voltage by supplied voltage. Rho into e to the power minus gamma L in the numerator. And in the denominator also, I'll take a Vs out. So when you take Vs out, you have e to the gamma L plus, not plus, sorry, it's minus rho times e to the power minus of gamma L. Okay, now let us proceed further. Let us try to substitute. Okay, so that means so VS cancels out here. So I have a Z naught into, okay, let me substitute it for a rho value. Okay, e to the power gamma L plus, what is rho? Just recall, we had an equation for rho calculated just now. So that is ZL minus Z naught by ZL plus Z. Let me put it back over here. So this is equal to, let me just show you the previous equation, where I'm substituting. So for rho value, I'm trying to substitute. So rho becomes equal to, this is ZL minus Z naught divided by ZL plus Z naught, rho value, into e to the minus gamma L whole divided by, this is e to the gamma L minus ZL minus Z naught divided by ZL plus Z naught into e to the power minus gamma L. Okay, now I take a common denominator in both the numerator as well as the denominator, right? So that is equal to Z naught into, so we have the term e to the gamma L as it is, right? So the ZL plus Z naught goes over there. Let me write it this way. So this is equal to ZL plus Z naught into e to the gamma L plus ZL minus Z naught into e to the minus gamma L. This is the numerator of the numerators, where I have a common denominator ZL plus Z naught. Okay, then whole divided by, in the denominator also you will be doing the same thing, right? So there is a ZL plus Z naught, ZL plus Z naught getting multiplied with e to the power gamma L. There is a minus sign, ZL minus Z naught into e to the minus gamma L. Denominator has a common denominator ZL plus Z naught. Is this okay? So this and this terms will get cancelled, right? I just have the numerators of both the terms. Okay, now I further try to simplify by taking the terms containing ZL together and terms containing the Z naught together in my equation. Okay, so this is equal to, let's have the Z naught as it is. So in the numerator, I can note that, see, there is a Z naught into this, Z naught into this, Z naught into this, Z naught into this. So all the Z naughts I'll try to write together first. Okay, in numerator first, maybe later in the denominator. I'll repeat the same thing for the denominator later. Then ZL into something, ZL into something. Once again, ZL and ZL, right? Whenever we multiply, I can take out ZL common and Z naught common. So that's my next approach. Right now we have e to the gamma L taken out common. So I want to change it. I will simply write the ZL common. So when I take ZL out, it's e to the gamma L in the first term and plus e to the power minus gamma L in the second term, right? Plus, take Z naught common. First term gives the e to the gamma L. Second term is minus of e to the power minus gamma L. This is what is happening in the numerator, right? Similarly, let me take a ZL out here. So I have e to the gamma L minus e to the power minus gamma L plus Z naught you try to take out. You have e to the gamma L plus e to the minus gamma L. Is it okay? Fine. Now, what we can do, okay, let's try to simplify further. I know something about this. If I have, yeah, so the term containing e to the power theta and e to the power minus theta, if you have a plus, that becomes a cos hyperbola. Okay, divide by 2 is required, but I multiply and divide by both numerator as well as a denominator by 2. So this 2 will be used by this one as well as this one. The 2 in the denominator will be used by the terms in the numerator, okay, to convert them into the cos hyperbolic and sine hyperbolic. Okay, so what I'm writing, I'll try to write here. This is the rule we are going to use now. If at all I see e to the power theta plus e to the power minus theta by 2, that is equal to cos hyperbolic of theta. Similarly, e to the theta minus e to the power minus theta by 2, if you see this term, you can write it equivalently as sine hyperbolic of theta. So we apply this particular rule in the above equation. Okay, so what we are calculating, we are still calculating the Z in here. So Z in is equal to Z naught into, okay, let me write what we have, ZL into e to the gamma L plus e to the power minus gamma L by 2. So that should be cos hyperbolic, okay, cos h of gamma L, okay, plus Z naught into, this is it sine? Yes, sine hyperbolic of gamma L, whole divided by ZL into sine hyperbolic of gamma L plus Z naught into cos hyperbolic of gamma L. Right? For simplicity, let us try to divide both the numerator and denominator by, say, cos hyperbolic, because sine by cos is tan. I can write a easier representation. So this is equal to Z naught into, yeah, so I have ZL plus Z naught tan h gamma L whole divided by denominator. The sine by cos gives you a ZL. I'll write a Z naught first. Z naught plus ZL tan h gamma L. So this is the equation. All right. So for calculating the input impedance using the, so in order to now it should be very clear. In order to calculate the input impedance, I need to know the characteristic impedance, load impedance connected, and the length of the line and the propagation constant, that is gamma. Okay. So if you know all these parameters related to the line, yes, you can calculate the input impedance. Okay, fine. Now also we have some of the cases to look at. So first we'll look at the cases. So case 1, we keep this, the equation we just got as a reference with us. So first one is a short circuit line. So I know that short circuit line will have ZL equal to 0. If the load is shorted, how do you identify that? Even the voltage becomes equal to 0 on the load end, isn't it? So in the above equation of Z in, you simply convert every ZL equal to 0. That is, this is 0, this is 0. Correct? So when you do that, what happens? What happens? What's the ultimate final equation? Can you tell me? Simply put, above equation, put ZL equal to 0. What do you get as the final answer? So you see ZL equal to 0. So I have a Z naught 0 plus Z naught tan h gamma L divided by Z naught. So Z naught cancels here. So it's simply Z naught. One Z naught is outside. Okay. So Z naught tan h gamma L. So this is the equation you are going to use if at all you see a short circuited line and the question is to calculate what is the input impedance. All right. Let's go ahead to case number 2. So in case 2, I'm going to look at the open circuited line. So I know that this means the ZL is infinity and there will be no current because of it's being open circuit. Okay, now can you do the calculation for ZL in this case? Remember what you did when ZL became infinity in one of the previous equations. Okay, I'll show you the equation for Z in, right, which you can see at the top. Substitute ZL equal to infinity and get me a simplified answer. Yes, yes, yes. Very similar thing, right? But I'm substituting ZL equal to infinity there, because of which I get infinity by infinity undefined. Okay, so yes, yes, yes. Try to take a ZL out and then you simplify. Yeah, what happens? 1 by tan, there will be a Z naught, I guess, right? So outside you have a Z naught, correct. Z naught divided by tan H of gamma, right? So by the basic definition, 1 by tan becomes a cot hyperbolic. Okay, so this is Z naught cot hyperbolic of gamma L. Correct. That's the right answer. Okay, we have another case to study here. That is a case 3. This is also very common in case of problems. That is a lossless line, right? If you remember, what is a lossless line? There is no, the gamma becomes a pure imaginary quantity, right? Gamma is equal to alpha plus j beta, where alpha is equal to 0, right? Just try to recall what we studied earlier. And gamma becomes equal to simply j into beta. So in the equation of Z in, now I make the changes. Wherever I have a gamma, I'll simply write j beta. Okay, fine. So that means you see I have a Z naught outside into, there is a ZL plus Z naught into tan hyperbolic of, there is no gamma. Gamma is replaced by simply j beta L. Okay, whole divided by, this is Z naught plus ZL into tan hyperbolic of j times beta L. So, but if you remember, we have one property in the one property of a tan hyperbolic function. That is, if you have a tan hyperbolic of j theta, tan h of j theta is equal to, this is how we equate, this will be equal to j times tan theta. Okay, so that's a one very important rule. Tan h of j theta is j tan theta. Tan hyperbolic can be converted into the simple tan function. So put it here. So that is ZL, not ZL, sorry, it's Z naught into ZL plus j times Z naught tan beta L all divided by Z naught plus j ZL into tan beta L. This is the equation for any lossless line. Okay. Now under the lossless line, I can have a short circuit or open circuit. Okay. So I'll simply write. So therefore, Z in of a short circuited line, you know the condition, right? So from the previous equation, I know that this is simply Z naught tan H of J beta L. I substitute and I get J times Z naught tan beta L, right? This equation I already have in the previous case, okay? Previously discussed short circuited equation will give you Z naught tan H gamma L. So I substitute gamma as J beta, I got this because right now we are discussing about the lossless case, okay? Similarly, if I'm looking at the Z in of a open circuited line, that becomes, just recall we calculated Z naught into cot hyperbolic of gamma L, which is J beta L, right? Here you have the opposite relationship. Cot hyperbolic of J theta is minus of J times, I have a Z naught as it is, into cot beta L. Okay, so cot hyperbolic of J theta is minus J cot theta. Is it okay? All right. Then let's proceed further. Then in this case, we have a case number 4. That is, this is the most widely used application that comes whenever the practical application is required. You use what is called as a quarter wave transformer. One of the widely used application in case of for stub matching and also in most of the communication circuits. Okay, so this is the transmission line with specific length. Length is equal to lambda by 4. So you see the quarter wave comes into the word quarter wave is because of its length. You use a transmission line whose length is equal to lambda by 4. Okay, now let's do the calculation here. How do we do that? Okay, we'll start with the Zn equation. There is a very peculiar feature. Okay, so Zn is equal to Z naught, and I'll write so ZL plus J times Z naught tan beta L, simplified version, whole divided by the Z naught plus J times ZL times tan of beta L. Okay, now we use something called as the equation of beta. So equation of beta says that beta is equal to 2 pi by lambda. If you remember, we use this, correct? The phase constant, one is the alpha was the attenuation constant, beta is the phase constant. So phase, right, is 2 pi by lambda, right? And you see L is already known for this particular case, lambda by 4. So calculate what is beta L. Beta L is equal to 2 pi times lambda divided by, right, 4 lambda, correct? So lambda lambda cancels, 2 cancels with this as 2. So your answer will be pi by 2, correct? So this is equal to pi by 2. So beta L, I can simply write pi by 2. Okay, so that is equal to, right? I think we have a problem here. Just check what happens when you put tan of pi by 2. What is tan pi by 2? Because beta L is pi by 2. What happens if you put tan pi by 2? Yeah, 90 degree, tan 90. Yeah, what happens? It's infinity actually, correct? So once again, that means I cannot put that value here. So you need to take tan beta L outside. So Z naught, take tan beta L outside, and then you write. So this is ZL divided by tan beta L plus J times Z naught in the numerator divided by, once again, tan beta L taken out from the denominator. So this is Z naught divided by tan beta L plus J times ZL. This is okay. Tan beta L cancels. Now you substitute. When that infinity goes to the denominator, that is 0, right? So this is Z naught into numerator, you get J times Z naught. Denominator, you get J times ZL. Correct? So what happens? JJ cancels. So this is Z naught square divided by ZL. So there is one very peculiar relationship that holds good for a quarter wave transformer, which is used for the impedance matching. I will show you how to use this when we solve the problems, but this equation is very important. So Z naught square is equal to input impedance and the load impedance. You see, this is a very peculiar relationship, right? Z naught is what? Characteristic impedance. Square of the characteristic impedance is input impedance into output impedance, right? Not output, sorry, load impedance. That means Z naught can be root of Z in into ZL. Very important. Okay, this is valid for quarter wave transformer only.